Okay, so here's video number 5, periodic trends. Definitely this is going to be the most challenging, only because they're periodic trends, and if you don't understand the trend, you're not going to understand what you're doing. So in some of the work that you were doing this past week, there was a little cheat sheet. It looks something similar to this. I've just kind of marked it up a little bit. I'm not expecting you, of course, to have to print it out, because that'd be ridiculous. But what you should probably do is maybe just write down a few little things like I did. Okay, so the most important thing is that you have marker elements. And this sounds really silly, and I'm probably one of the only people that says this, but for me, this is the way that I learn things, and you all know I'm a very visual learner. So when it comes to our periodic trends, there's francium and fluorine. They're basically two of the only F elements on the periodic table, besides FL down here, but don't worry about that one. Okay, so if you'll notice, the reason why the FR and F are so important on the periodic table is if you were to look at yours, which is a little bit larger so you can actually see them, fluorine is all the way over here and francium is on the other end. So notice they're on two opposite sides of the periodic table. Why is this important? Well, you're going to notice that when you start to look at your periodic trends, that's what happens with your trends. Either they go all the way over to the left and down, or they go all the way over to the right and up. Okay, which means that your marker elements are these two elements on the periodic table. So notice I've even colored them in so that I can see that if my element is closer to francium, when I'm talking about radius for either atomic or ionic, I know that that element has the largest radius on the periodic table. If my elements are closer to fluorine, or in this case helium, but we'll talk about that in a minute, or fluorine here, that element is going to have the greatest electronegativity or ionization energy. So knowing those little cheats really does help. And of course, since we're not in class together, I couldn't have shown these to you, but that's what you really want to focus on, are those elements, FR or F. Okay, now, with that being said, what else do you need to understand? You need to understand what these things are telling you to do. So with atomic radius, you're talking about the distance between, basically, don't worry about all of this, the nucleus and the outermost valence electron. Okay, and then with ionic radius, you're talking about the radius of an ion. So remember, an ion is something that's charged. You either have a cation, which is a positive, or an anion, which is negative. And if you're a +1, that means you've lost an electron. And if you're a -1, that means you've gained an electron. Okay, so we'll come back and talk about those each in a second. And over here, you're talking about something called electronegativity, which means attracting an electron. You want an electron. And down here on ionization energy, you want to get rid of an electron. So now here's the most important thing. Actually, not, sorry, let me go back. You don't want to get rid of an electron. It's how much energy is going to be required to actually take an electron from you. So let me explain these two, because I think these two are easier, and then I'll come to these. All right, so when it comes to electronegativity, all right, you are talking about the energy of attraction. Okay, and in this case, in chemistry, attraction is huge because you all know that if you have an attraction for something, that means you need it, an affinity for it. You want an electron. Okay, so we all know, based on everything we've done thus far, that everybody in the halogen family is extremely reactive because all they want is one more electron. They get one more electron, they're a noble gas, and they are happy as can be. Notice fluorine, the arrow stops at fluorine. Down here, if you talk about ionization energy, the arrow actually goes past fluorine and goes to helium. So this is a huge denotion or note to make, something to that effect. I didn't major in English clearly. But in this case, fluorine wants an electron. The noble gases do not want electrons, so they have no electronegativity. So if a noble gas is ever on a question that says what has the greatest amount of electronegativity, a noble gas will never have electronegativity. So you can almost cross those guys out for electronegativity. They will never have electronegativity. They will never attract an electron because they already have them. They're already perfect. So when you talk about fluorine, versus all of these guys. Now, of course, fluorine's going to want an electron, and he's going to have the greatest attraction for electrons over anyone below him because he has the fewest number of electrons. Because he has the fewest electrons, he's going to have the most affinity or the most wanting of an electron. He only has 9, he wants 10. Whereas chlorine has 17 electrons. If he gets one more, he gets to be a noble gas. But guess what? If he loses electrons along the way, which hopefully he never does, but if he does, he still gets to look like neon. So either way, he has a chance to be a noble gas here, here, or even here. Same thing with AT. If AT were to, for some reason, lose electrons, something takes his electrons away, look at how many noble gases he still can look like. So his attraction of electrons is going to be much less than if you talk about fluorine. Fluorine, if he loses electrons, he only gets to look like helium, and no one wants to only have 2 electrons. Sorry, helium. So the attraction for electrons is greatest at fluorine. Any element on the periodic table, I could put 7 different elements on here. Whichever element is closest to fluorine is going to have the greatest attraction. Now, if I had oxygen versus sulfur, clearly oxygen is going to have a greater attraction because oxygen is closer to fluorine. But what happens if I had oxygen and chlorine? Okay, they're both close by 1 block. Okay, well, then it goes to the rule of groups or families. Oxygen is not in the family there, but chlorine is in the family here. So technically, chlorine will have a greater affinity or an attraction for an electron because it just needs 1 more. Oxygen would need 2 more. All right. Now, generally speaking, I'll try not to do that to you on a test, but you never know. You might see something like that, and that's the general rule is if it's close like that, then you go with family. Families will win over anybody. Okay, which then brings you to ionization energy, which is basically the exact same thing. So when you talk about ionization energy, it has the exact same trend as your electronegativity. The only difference is now instead of it being the ability to attract an electron, it's the energy that's required to remove an electron, which means let's take an electron away from something. So if there's anyone on the periodic table that doesn't want to lose an electron or let an electron be removed, it's going to be your noble gases. And that again is why the arrow on this one goes all the way across to the noble gases, whereas if you looked up at the one on the electronegativity, it's stopped at fluorine. So when we're talking about ionization energy, this one is going to be the highest in your noble gases. Electrons never want to be removed from a noble gas. It's already in its most stable form. There'd be no reason to take one away. All right. Fluorine, of course, and all of everybody in his family, why would you want to lose an electron? You want to gain an electron. So because of that, their energy is also going to be high, but clearly not as high as the noble gases. And then you lose energy as you go across because, of course, these guys, they want an electron to be removed. Because if you remove an electron from sodium or potassium or any of these elements, they're going to be a noble gas. So as you go from right to left, from left to right, as you go from left to right, the energy to remove an electron increases, just like in electronegativity. As you go from left to right, the attraction of an electron increases, except you stop at the halogens here, you stop at the noble gases here. Now, with that also being said, the same is true for going and starting at the bottom to top. Okay, so as we said earlier, AT has way more electrons and can become any of the other noble gases. So because of that, his attraction for the electrons is less than as you move up. Same thing here. Okay, AT, think of like a dog walker. And this is the usual example I give, and it's probably the most hideous example I can give, but it makes sense in my mind. AT, that'd be like having, well, gosh, I just went blank because AT's number, 85 I think it is, electrons. Okay, think about having 85 dogs, okay, as you're walking them, versus 9 dogs. You're not really going to notice if you lose 10 or 20 dogs. Okay, and that sounds like a lot. If you lose 10 dogs, oh well, it makes it a lot easier to walk those dogs. But if you lose 10 electrons here, you're going to lose half of your electrons, you're going to lose all of your electrons, and you're in trouble. So as you go up, the energy to remove an electron also increases because you're losing your electrons. And these guys, again, don't want to lose electrons. The less electrons you have, the less you want to lose. It's kind of like money. If you only have $2, you don't want to lose those $2. All right. So ionization energy and electronegativity, same trend as you go up and as you go across. As you go up and as you go across, they increase. So obviously it would be exactly the opposite, which is why I told you guys about the marker elements. If you look at francium, francium is on the exact opposite end of both of these trends. So greatest, least. So this would be least electronegative and least ionizing energy. Okay, hopefully that makes sense. I'm going to talk about atomic radius and ionic radius next on the next video.